Hi, welcome to Quantum Physics for Non-Physicists. And this is lecture 22. And today is the 1st of December, which is also the first snowy day. Okay. Here we go. Okay, so today we'll continue talking about quantum thermodynamics. So in particular, I finally introduced what the quantum thermal state is, and we'll go over some properties of this. And then we will start with quantum heat engines. Yep. And our daily analogy today is a very familiar experience, which is to have, for example, a set of earphones with cables, and you put them in your pocket, and then an hour later, when you take them out of the pocket, they're all tangled up. Right? So in particular, if you looked at any small subsystem here before, it would be very, very neat. But if you look at any subsystem after, it will be a mess, right? And of course, if you have time and you have access to the whole thing, you can slowly unentangle it. But if you don't have access to a small thing, it's very hard to make heads and tails of it. The same thing, exactly the same thing, happens to quantum systems in an even more dramatic fashion. So even if you start with a state that is the equivalent of this very tiny thing. So for example, if you have a product state over many subsystems, such that even if you looked locally, you could see a pure state. Now, if you let it evolve, under some Hamiltonian for some time, for most Hamiltonians, for most times that are long enough, at the end, the result is going to be a global state that is highly entangled, which means that if you look at any subsystem, you no longer have a neat pure state, but you'll have something that looks a bit more like this. So it will look very, very mixed. Okay. And in particular, this is how thermal states occur in nature. So we start with something that is very, even if you prepare a state in your lab and you're very, very careful with what you're doing, then if you wait for long enough, at the end, the final state will be such that each subsystem is going to be very mixed. So we'll see this in more detail a bit later. So what did we do in the last lecture? So first, we went through this idea of operational thermodynamics and just start from this idea that we can have heat engines that operate between two baths at a hot temperature and a cold temperature. And we didn't even know what this is. We don't give any explicit model of what a bath is. But we just say, well, these machines, it will take some energy Q hot from the hot bath. It will deliver some energy Q cold, so some heat to the cold bath, and in the process it will produce some work. And we saw that for reversible engines, the best possible efficiency, so the work divided, so energy that is useful divided by the energy that's consumed, was this ratio of the temperatures of the hot and cold bath, which is always smaller than 1. We never gave an explicit model for the state of the bath, but this is what we'll do today. So I'll introduce you to a candidate state for a thermal bath. So a density matrix that depends on the temperature. We'll look at some properties of this, and then we'll test if this is indeed a good thermal state. And the way to test it will be, we'll build a reversible quantum heat engine, okay, just like this. And then we will run it, and then we'll compute the efficiency, and we'll see if the efficiency comes out as a ratio of the temperatures in this way. Okay. So that's the goal for today. But the first part of the lecture will be just looking at properties of this thermal state. So what's the quantum thermal states? So let's suppose we have a system A, has some Hilbert space and some Hamiltonian, right? Which you can always write in the eigenbases of the Hamiltonian, meaning, so these are the energy eigenstates, and these are the corresponding eigenvalues, which correspond to the value of the energy. Then, and there are many ways of deriving this thermal state, which we'll do in detail in the lecture Advanced Topics for Quantum Information Theory, but not today. So a thermal state that depends on the Hamiltonian and on the temperature is just given by this. So what's on top here it's an exponential of the Hamiltonian with some factor that's a constant, and here's the inverse of the temperature. And down here is this normalization factor. We'll look into this. So let's just write it as explicitly in the eigenbasis of the Hamiltonian. So just replace this HA with this thing here. Then what we obtain is this state. So it's a probabilistic mixture of all the energy eigenstates, but each eigenvalue is now the exponential of the energy with this negative exponent that depends on the inverse of the temperature. Yep. So how does this look? We can represent it like this. So suppose that this is the energy, and these are all the energy eigenstates. Okay, so we just place them where the eigenvalues of the Hamiltonian are. And then you can represent it by putting these little balls of different sizes, where the size of the ball is proportional to what is called the occupation of this level. So the probability that the state is in this level, right? So if you made an energy measurement, if you measure this observable, the Hamiltonian, what's the probability of getting this outcome? E0, E1, E2, E3, okay? So it always looks like this. So it's kind of fatter at the bottom. So this is the state that is most likely to be occupied, so that define the system. If you measured it, would be in this state, and then with increasingly lower probability, depending on this spacing and depending on the temperature, you get the other states. Right? And it's important to note that this is not a superposition of all of this. Okay, it's really a probabilistic mixture. So it's really like you shuffled it, and with some high probabilities down here and with some lower there and so on. Yep. And so this probability of finding the system in some energy eigenstate EI, it's also called the population of the level. Okay, this is a term that physicists use a lot. So population of the energy level EI, for example, or occupation of the level. It's another term we use. So let's just look at some notation. So first of all, we may not always want to write this whole thing, that the state, that's a density matrix. I call it T, like tau for thermal, and that it depends on the Hamiltonian, on the temperature. Sometimes the Hamiltonian is obvious, so we just write TA of the temperature, and sometimes even the temperature will be obvious, so we just write tau A. Okay. This KB that appears here, this is a constant, it's called the Boltzmann constant. Don't worry about it. We could always, it's there for historical reasons. Of course, we could always rescale what this value T is and obtain different KBs. Right? But historically, this is the one that's been used. Sometimes one tries to omit the constant completely by just defining this new variable beta, which is KB over T, which you call the inverse temperature, and then you get tau is E2 minus beta H A divided by Z, right? Good. Now, this Z, it's just a normalization factor, right? So we want that overall, this map here has, this operator has trace 1, okay? And this is an exponential, and the eigenvalues of this will depend on the eigenvalues of the Hamiltonian, on the temperature, on this constant. So in principle, it could have any trace. So just divide it by the trace of this operator, which is, again, what is it? Well, it's just the sum of these exponentials of the eigenvalues. This has a name. It's called the partition function. And it's because the state has such a simple structure, right? It's just a function of these two variables. Sometimes many of the properties of the state are encoded in this partition function. Okay? So we see a lot in statistical physics, for example, that people don't even work with a density operator, which is a big matrix. They just work directly with this number to find out some properties of the state, like the average energy, for example. This can be derived directly from this function. Okay? That's why it has a name. That's why it's important. Okay, so let's look at some examples first. Some extreme examples. So that's the general form of the state. This Z, again, depends on H and T. So let's look at some special cases. So For starters, let's see what happens when the temperature goes to 0. And this is really the absolute 0. You can think of it as the absolute 0, because what happens then is that, well, this goes to 0, so this thing goes to infinity. So you have the exponential of minus infinity of this matrix. So if you look, you have something like this, okay? Which means that for all terms where this EI is larger than 0, this is going to be very, very small, so it's going to tend to 0. So the only remaining term is the one corresponding to the ground state of the Hamiltonian, so to the lowest energy eigenstate, okay? Which is why if you see sometimes people talk about cooling a system to the ground state, right? What does this mean? It means that if you have like a thermostat, and as you cool it, like the probability that the system will be in an excited state, so a state of high energy, goes to 0, and then at the absolute 0, if you could go to the absolute 0, which we never can, then it's for sure it's in this state, okay, in the ground state. And a lot of efforts into cooling systems is precisely to try to get them to stay in this ground state. In the opposite end, so of the scale, we can see what happens when t goes to infinity, that this exponent here goes to 0. So at infinite temperature, this goes to 0, which means that all the terms here have exactly the same probability. So what you end up with is kind of a fully mixed state. So a mixture, an equal mixture of all the energy eigenstates. So the system is so mixed that it's equally likely to find in a state of high energy as in a state of low energy. I mean, of course, this is not physical. You never get infinite temperature again, right? But you can see how close you're, in practice, to get close to this. And in this case, the Z also goes to just the dimension of the system. Okay. So in general, if you have a hot temperature compared to a cold temperature, the difference will be that at the hot temperature will have more occupation in states of higher energy compared to the cold one. So the cold one will look closer to this ground state here. Okay. And in particular, if you look at the average energy, it would be for the hot one will be somewhere there, whereas for the cold will be much lower. Which makes sense, right? So a hot system has more energy in it than a cold system. Okay. And now you may think that for fun, like forgetting about physics, you may think, well, there's a t here. This is just a number. What happens if I make it negative? Okay. So if you make t smaller than 0, then what happens is that the states of higher energy are more likely than the states of lower energy. Okay. So this is not a thermal state in the sense, it's not a state that appears naturally in nature a lot. Okay, except in some very, very special cases or for a very short time before it kind of relaxes to something that looks more like this. However, you might want to engineer this on the lab and then just call it like a state of negative temperature. Okay, we'll see that this is the case for when we build a heat engine. In particular, we'll have a little subsystem that has kind of a negative temperature. Okay, and when you have something like this is called population inversion, meaning that the states of higher energy now have higher population. So we'll see examples of this later. So what are some applications directly before looking at more properties of this state? Let's just see some applications of thermostats. And the main idea is that this idea that systems in nature, if they're in contact with some environment at some temperature, they'll tend to thermalize. So they will tend to go to a state that looks like this. So one big application of this is quantum chemistry, where what's your goal? You want to know if I change a molecule, so if I change the Hamiltonian of a small system or of a material, for example, I don't know, I'm trying to make a new metal or a new semiconductor or not. I want to know how it behaves, right, in nature, which means essentially how does the thermal state behave? Okay. So then what we can do is to try to find the low energy eigenstates. So just like the first three eigenstates, for example, and this gives you an approximation of how the thermostat works for small t, for small temperature, right? And from this, you can try to find what the behavior of these molecules is. And so some applications that people have in mind are, for example, nitrogen fixation. So this is the problem of trying to build better fertilizers for the soil. So molecules that capture nitrogen. This is one big field of research. So again, the idea is to try to use quantum computers to find what these low energy eigenstates are, so that then we can test different candidate molecules and try to predict how well they behave. Okay. And the other big application that people have in mind is molecules for pharmaceuticals. Again, right? You're looking for a certain behavior, you tweak the Hamiltonian a bit, you try to find these eigenstates, and so on. Another big application is this idea of adiabatic quantum computing. So what's the idea here? So you can take a classical problem and try to encode it on the Hamiltonian of a system. So for example, a very famous problem in computer science is this 3-set. So this is a problem where you're given a big formula, like a Boolean formula, like a logical formula, where you have, for example, x1 and x2 and not x3. So these are 3 terms, and x3 or not x4 or x5 and something else, and so on and so on and so on. So you have a number of these clauses of 3 elements each, and you want to know if there's any assignment of the variables that satisfies that gives an outcome of true for the whole formula. This problem is NP complete, which if you're a computer scientist, then you know that this means that any problem in NP, so any problem whose solution can be checked quickly, can be written, can be reduced to this kind of problem, right? So if you can solve this, then great. Okay, so what does this have to do with quantum systems? So the idea is that you can encode this kind of problems on a Hamiltonian, on a construction of a Hamiltonian. So in this case, you build a Hamiltonian that's the sum of local terms. So imagine that you have like 3 qubits, and just like x1 could be a bit that could be 0 or 1, you have this qubits that could be in state 0 or 1 or a superposition thereof. And then you build these local interactions between, for example, x1, x2, and x3, such that the low energy state is the one that satisfies these constraints. For example, x1 is 1, x2 is 1, and x3 is 0. You just build it like this. And then you go on to the next formula and you build another local interaction, okay? And the next, and the next, and the next. And then you build all of this, you just say, okay, now I have a Hamiltonian that's a sum of all these parts. Okay? And now the question of, is there a state that satisfies, is there an assignment of x1, x2, and so on that satisfies this, is the same as, and I'm not proving this exactly, but this is something you do in quantum computing course. So this is the same as saying, what's the energy of the ground state of this Hamiltonian? Okay. If all these terms can be satisfied at the same time, then the whole Hamiltonian, there is a state which corresponds to this assignment that has very low energy. If not, then you can never reach this such a state, and then the ground state has high energy. Okay? So then you think, okay, so then the problem is just kind of taking this matrix and finding the ground state. But this is a hard problem because this is in general can be a very large matrix. Okay, and finding the ground state means you need to diagonalize the matrix, and that's a very hard problem to do on a computer. So what's the idea of adiabatic quantum computing is that you start with another Hamiltonian, not this, but we start with a Hamiltonian that you know well, and you know the ground state, okay? A different one. And then you cool the system to a thermal state of very low temperature of this. So you know that it's approximately on the ground state of your first Hamiltonian H0. Okay? And then over time, you tweak the Hamiltonian according to some parameter t, very, very slowly, such that your constraint is that the initial states, the initial Hamiltonian should be the H0, and the final Hamiltonian would be your goal, the one that encodes your problem of interest. This can be done, for example, I don't know, you turn some magnetic fields in this qubit, around these qubits at the right time, very, very, very slowly, okay? For example. And if you do the idea is that if you do this very, very, very slowly, and you always let the system kind of cool down, then the system will always be close to the ground state. So you can map like here you can map here over time, what is the energy of the state that you have. So it's the energy of the thermal state corresponding to the Hamiltonian of the moment and the low temperature, right? Which should start with the known thermal state, and then as you change it, it can change. And then depending on the solution of your problem, it will either end up being very small or it will end up being very large, right? So then at the end of this change of the Hamiltonian, then you measure the energy of your final state. Okay? And then you see that if it's high energy, then you know that this problem could not be solved. And if it's low energy, then you know it could be solved. Okay, so these are two applications of quantum physics in quantum computing, which in particular use this idea of a thermal state. So what are some properties of this thermal state? And some of these you proved in the tutorial, some of them we will prove in the lecture in the next semester, in the advanced topics lecture. Okay. One you showed in the tutorial last week is this composability, which means that if you have a global system composed of many small systems, and you have a total Hamiltonian that is non-interactive. So you have one small Hamiltonian for each subsystem, okay, and then you just sum them all. Then in this case, your global thermal state of a temperature T is just the tensor product of the individual thermal states. So it looks kind of like this, divided by the normalization. Okay, this partition function. Okay. So it's actually a bit stronger than this. So if the global system is thermal and it's non-interacting between subsystems, then any subsystem is also thermal. Also, if I have let me get this state. Another even stronger property is that if I take any kind of subspace, so if I consider only two of these levels, then the ratio of the population of the two levels is still going to give me a thermal state. But if I reduce to just these two, then this population compared to this is going to be an exponential depending on the energy difference between the two levels. And this is also approximately true if you have a Hamiltonian that is like this, plus some weak interactions between the kind of neighbor systems. Okay, so a more physical Hamiltonian. And this is something we'll prove later. Another, maybe the most important property is that it's a typical thing. So like I've been saying again and again, many systems do thermalize. Okay, so my coffee, for example, now is getting a bit cold because the room is a bit cold. What does this mean? That in practice, that means that for many natural Hamiltonians, natural global Hamiltonians, and this normally means that you have so for example, here you have many particles, and you have lots of local interactions. So this would be like local terms of the Hamiltonians. So another example is a liquid or even a metal where you have little atoms sitting on a lattice and interacting only locally with each other. So if you have many local interactions, and we start with a pure state, even if you start a pure state that we know and we wait for long enough, which means that you let it evolve under some Hamiltonian, under the global Hamiltonian, then most subsystems that are small enough will appear to be thermalized. Okay. Of course, that the global state is still pure, right? It's just a unitary applied to a pure state, so it's still a pure state. But if you look at any small enough subsystem, it will appear to be essentially a thermal state. So this is, again, if you think of the analogy in the beginning, if you leave your headphones in your pocket and then look at a small subsystem, like a small piece of it, then it will look tangled up. Okay, so that's the idea. The global state is going to be so entangled that any small subsystem looks very, very mixed. And in particular, it looks like a thermal state locally. Okay. So again, so if I have my system of interest, that's my cup of coffee. And of course, I have the environment, for example, the air inside this room. Maybe this chamber was specifically designed for me and it has a pure state over the whole atmosphere, which is very unlikely. But even so, like the system of interest, so meaning the molecules that are around my cup of coffee that are interacting with this are approximately thermal. Okay, and what this means is that if I take the global state at the time t and I trace out most of the environment and I'm left only with my little system of interest, then this will approximately be a thermal state. And the temperature of this thermal state depends on what? Well, it depends on the energy of the global state. Again, like we saw before, hotter systems have higher average energy. Okay. The other thing that we'll prove in the next semester is this idea of passivity, meaning like we saw in the previous lecture, we could not extract work from a single heat path. And this will be the case here. We'll look at an example a bit later, but let me just give you an intuition. So the thermal state, this kind of exponential state with increasingly lower population for high energies, is the only state such that if you have access to many, many copies of this in whatever systems there are, you can never extract energy from it in an ordered way. So what's the intuition? So you remember this example from a few lectures ago, where if you had a small system that we know is in an excited state, okay, it's not a thermal state, and we had this battery, we had this battery at some level, and this battery was made by this Hamiltonian that looks a bit like a ladder, right? So our goal is to raise this this population, so to raise this weight. We saw that we could apply a global unitary that was energy conserving on the global system, so it commuted with the global Hamiltonian that lowered this state and raised this, okay? And thus producing work, because work is what we say if we have, well, we have a big difference in energy from the initial state to the final state, but it's not very spread out. And what happens if we have these thermal states is that we cannot do this. First of all, they are the higher probability lies with the lower energy. So the probability that if I apply some operation like this, most likely what would happen is that this would go up and then this would go down. Okay, but it's also so that even if I have many of them, if I choose any qubit, even among different systems, then it's still a thermal state, right? It's still going to be a thermal state. And it doesn't matter what operation I apply that is energy conserving on the whole. What will happen here is that either it lowers the energy of the battery, or it can indeed end up with some mass here and something here, but then what will happen in the battery is that it will be too spread out. Okay, so it's no longer considered work, because if I want to later use this battery for something else, then I don't know what energy I have there. Okay, we will look into this into a bit more detail in some examples later. Okay, So now we can start thinking about what we want from a heat engine. So what are the resources at our disposal? Remember before we had a hot bath, a cold bath, some internal mechanism of the engine, and then it produced some heat, some work, sorry. Okay, so we're going to take a hot bath, which means any system. We're going to say for now that we can build any Hamiltonian we want, and temperature Th, which is hot, and we're going to put it in a thermostat. Then we do the same for a cold bath. So we take, again, any Hamiltonian, and we put it in a thermostat of temperature Tc that's smaller than T hot. Okay. And we're just going to assume that we can always, maybe these baths are in contact with a larger bath, and we're going to say that we can always thermalize them for free. Okay. So this one will always stay in this stage. We might take some energy from here, but then if you wait long enough, it will go back to this because it's in contact with a larger bath. Okay. And then we have some battery, which was again this kind of system. And let's say it starts in state 0. And what's our goal? Well, it's to raise this energy without spreading it out too much. Okay. So we want that the difference on average energy and the battery between the initial state and the final state is much larger than, much larger than the spread in energy. Okay, so this delta E is the variance of energy. Okay, so an example, this should be good. So there's a 0, here's the final average energy, and maybe there's like with small probabilities also around there, but there's enough of a gap that we can measure this. This is bad if it ends up being like super spread out. Okay, good. And for our engine itself, we can choose any Hamiltonian we want. Okay, and we'll try to trick this, see what Hamiltonian we want for the engine here. And the initial state should not matter much, because what we'll do is that we will connect parts of this engine to the hot bath, so it will thermalize that part, and we'll connect parts of the engine to the cold bath, so it will thermalize that, and the other part of the engine will be connected to the work. And then we want to build a global Hamiltonian that's going to be just a Hamiltonian of all these systems independently, plus some interaction, which corresponds to turning on the engine. I let it run, and then let it run for some time, and then we see if it works to do this. Okay. So before we continue to a specific example of an engine, let's take a break here, and we continue at 10:35. Okay. So let's make a break. Okay, so let's continue. And I was not too happy with the way the second half of this lecture went, so I'm recording it again. And so let's continue. So we'd seen that we want to build some heat engine like this. So we'll have some internal mechanism, and it will have some connection to hot and cold baths. And then eventually it will want to raise this weight, right? So we'll start by looking at some explicit mechanisms, but we'll start with a very, very simple case of something that doesn't do exactly this, but it has already some of the dynamics that will make sense later. Okay, so let's take the smallest possible case. So we take an engine that's just made of 2 qubits. Okay, and we take the smallest, the simplest possible case again, where we have 2 qubits that have kind of the same energy gap. Okay, so this is the Hamiltonian is just the sum of the Hamiltonian of the first qubit, which is just 0 energy for the state 0 and energy E for state 1. Okay, times the density in a second plus the Hamiltonian of the second qubit, which is exactly the same. Okay, so overall it looks like this. So when I make this kind of drawings, I always mean that here is like kind of the energy of each individual state. So of the first first qubit and the second qubit. Okay, and I always say that initially we had connected this this first qubit to a hot bath. Okay, so it went to some kind of thermal state, which I represent like this. So there's some probability of being up here. We'll look into this in more detail later. And the second one to the cold state, to the cold bath. Okay, so the same, but with smaller probability of being in the excited state. And now I will turn on some interaction Hamiltonian. So I want this interaction Hamiltonian to conserve energy between these two things. So it will be very similar to what we saw when we first introduced this work batteries. So what I can do to conserve energy, well, I can say if I raise here, I will lower there. And if I lower here, I will raise there. Okay. So this corresponds to this kind of, so this term corresponds to this interaction here, to this transition here, where I go from 0, 1 to 0, 1, 0, 1, go up to 1, 0. And the green one corresponds to this interaction here, right? Which is the opposite. I go from 1, 0 to 0, 1. I always need both terms because I need my Hamiltonian to be Hermitian. So the transpose conjugate must be the same as this. And, you know, in general, we can have some factor here. It doesn't matter. So this gamma is just a number, a real number that will tell me kind of how fast this interaction acts. Okay? And we will analyze this in some details, so not in full detail yet, but just to give you some intuition. So first of all, we will look at exactly what the joint global state is, but what's the probability of this state? So the first qubit being excited, it's going to be proportional to this, so the population of the overall level. Of course, it's going to be divided by the partition function. And the same is going to be true for the second one. And the idea here is that, well, if the temperature here is lower than this one, then it's going to be more likely that the particle, that the two qubits are initially in the red state, so being in the green state, this one being excited and this being in the ground, then the other way around, right? Just from the fact that this population here is going to be larger than that. Which means that if we run this Hamiltonian for a while, then this green transition is kind of more likely is going to have a larger weight in the end than the red transition. So this will result in kind of an energy flow where this particle is more likely to go down than to go up, and the other way around here, which means that energy is lost in this system and is gained on this system. Okay. Which, if you think about it, it makes sense, because think of this as like being a very simple model for a hot body, a hot system, and this being a very simple model for a cold system. Okay. When you bring them together, of course, the hot system will get a bit colder, so it will lose energy. And of course, the cold system will get a bit hotter, so it will gain energy. Okay. So that's kind of the idea. And this machine, for now, it's not storing work or anything. It's really just sending heat from this hot body to the cold one. So just sending energy from one to the other. Okay, so let's just see it in a little bit more detail. Again, we can take this Hamiltonian and just expand these identities and see what we end up with. Okay. So we have that this state has energy E, and this state has energy E, but of course we're interested in the global states of the system, so they can be either both down, or one up, one down, the other up, the other down, or both up, right? And what are the energies? Well, if they're both down, the total energy is 0. If only one of them is up, this energy is E. And if both of them are up, the energy is obviously 2E, right? It's just the sum of the individual energies in this case. Okay, what is our initial state? Well, the initial state is just the thermal state of the first Hamiltonian with temperature T hot, and the thermal state in the second with temperature T cold, okay? Which you can write, because there's only 2 levels, we can actually write down all the levels, right? So 1 over the partition function on the hot one, and then e2 minus k th0, so that's 1 here, 0, and e2 minus k over th e, the energy, 1. Okay, and the same thing on the second qubit, except the only difference is here the cold temperature, and here the partition function for C. Okay, so now we have like these 4 terms, 1, 2, 3, 4 terms, and we need to multiply them together to see what we end up with. And of course, we multiply these 2 functions, so this is just this factor at the beginning, and then we have the 0, 0. We have for the second one, what matters here is this occupation of the second excited state. So we have Tc here, the other way around for T hot for 1, 0. And if you have both of them, then you need the sum of these 2 probabilities, right? Because you multiply these things for both. So what's relevant here is that this is a matrix that's diagonal in the same basis as the Hamiltonian, as the original Hamiltonian, right? So when it evolves under the original Hamiltonian, only nothing happens, like we saw before for pure states. Okay. Nothing relevant happens that will matter for considering, for example, the final energy. Yep. So what we have for now. So suppose that we had these 2 things connected to the baths originally, but now we disconnect them and we only run like these 2 Hamiltonians. And these 2 Hamiltonians you can do as an exercise, see that they commute. Otherwise, you wouldn't have conservation of energy with the second one. Okay, so in this case, the evolution is e2it over h bar, the total Hamiltonian. But because these 2 terms commute, you can, we saw before, you can split this exponential as a product of 2 exponentials, okay? And we can worry only about this term for now, because this one will act kind of trivially. Okay. And here's a disclaimer. If you want this to be a real heat engine, we will keep each of the qubits, in addition to this interaction, we'll keep each of the qubits connected to a bath, and there will be some interaction between each qubit and its own hot or cold bath. But for now, we don't know how to model this. Okay, we'll model this in the next lecture or the lecture after that. So we'll see how to do this later. Okay, good. So now the density matrix at the time t is the original density matrix times this evolution, right, on the left and on the right. And we will look at only this term here, okay? Because again, this term will not do much. Okay. And remember that what we're expecting is that the green transition will happen more, and therefore there'll be kind of an energy flow from one to the other. Okay? Now, there's many ways to evaluate this, and we will do a more precise analysis of this once we have how to model the couplings. But for now, we can already do kind of an approximation. So what we'll do is just say, well, suppose we have very small time, or this parameter gamma in the Hamiltonian is very small. So then what we can do is just approximate this exponential as identity minus the first term, right? Okay, so if we did this, then this evolution here, well, it corresponds to this state here being sandwiched with this on one side and the complex conjugate of this on the other side, right? And then you have 4 terms. So where we have identity on both sides of row 0, then you get just row 0 again. Okay, so nothing happens. Then you have these 2 terms where you have identity, for example, on the right, identity on the left of row 0, and then the thing on the right, where this is the complex conjugate of that. And you have the other term where you have the identity on the right and that thing there on the left. Okay. We will not worry about these terms for now, because what they do, so if you look at it, so you have rho 0, and then you can, rho 0 is diagonal in this basis 0 0 1 0 1 0 1 1 1, and what this does is kind of shifting just from either the cats or the brass from 1 0 to 0 1 and vice versa. So this will produce some off diagonal terms, which for now we don't care about, because they will also not contribute for later. If you look at the energy of each subsystem, they will not contribute to this. Okay, there's an non-trivial analysis of this, but it's a bit too much for the outcome that we'll get here. Okay? But then you get the other term where you have this on the left and on the right of rho 0. Okay, so then you get the square module of that. There we go. And then we have this on the left and this on the right. Okay, and there's the rho 0. So we'll just look at what's happening here. Okay, so this thing just goes there. And then I just rewrote rho 0 with what we had before. So this is rho 0, right? And I just helpfully colored the different terms, okay? So this is the term that will kind of give a non-zero inner product with that, so I colored it red. And this is a term that will give a non-zero inner product with that, so I colored it green. Okay, and the same on the other side. Okay. And this corresponds to this red population and the green population. So what happens here in this product? Well, these two terms go away because they have inner product 0 with all of this, and then the only terms that survive is kind of red, 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 and green, green, green. Okay. And what this gives us is a factor of like this 1 0 1 0, which now is the same factor as before we had 0 1 0 1. Okay. And this corresponds to what? Well, you took the second qubit and lowered it, and you took the first qubit and raised it, so from 0 to 1. So this corresponds to kind of heating the first qubit, so the hot bath, and cooling the second one. Whereas the next term corresponds to precisely the opposite. Okay. Now, of course, that if this hot temperature is larger than the cold temperature, then this number will be larger than that. Okay. So overall, what did we end up with? So we start with this, right? We had the rho 0, we had these off diagonal terms that we don't care about for now. And then we had this term that depends here on time square and gamma square, which should be very small, but where you have this factor that where heat goes in the wrong direction, and this factor where heat goes in the right direction, kind of. Right? Good. So then we can just expand this rho 0 again to see what happens. So to these two terms, 0 0 and 1 1, nothing happened. But to the 0 1, we added this thing, and to the 1 0, we added this part here. Okay. So now, if we compute now what's the energy of the first system at the end, okay, so it's going to be trace of H1 and then the reduced state on the first qubit. So it's going to be taking the partial trace over the second of this thing here. Then we get that it's going to be this E1 minus this term here. Is that correct? Sorry, minus a term that will correspond to the difference between the two. And the same for the second one. So if you're going to see, if you compute again this thing, which we'll do in the tutorial, then we'll see that this energy is raised by some delta H, which will depend again on the ratios between the two, between these two terms. Okay. Good. But now, even if we had not done this whole analysis, we could already say a few things, which is what we'll do in the more complicated cases. Okay, so first of all, what was the probability of having these green dots? So the initial state necessary for the green transition, it was 1 over the partition functions, and then this this probability that the first state is excited, right? So that's this thing. And for the second one, it's going to be that. In order for the green transition to be favored, you need that this probability is larger than that, which in this case means that, you know, this value is larger than this, but the only place where they differ is these temperatures. Okay, so this corresponds to this TH being larger than TC. Now, if we want reversibility, so it means that we could run this this engine in reverse, then we don't want there to be any energy that's stored somewhere, like in correlations between the two systems, which is something that happens a bit more dramatically if we're not very careful in later, more complicated cases. So in this case, what this translates to is that we want indeed TH to be larger than TC. So we want the green transition to be more likely than the red one, but by very, very, very little. Okay, this corresponds in the macroscopic case to doing things very, very, very slowly in order for them to be reversible, right? So you don't go and push a gas very fast or let it expand very fast. You go very, 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 very slowly so that there's no energy loss for other places. Okay, so in this case, it will correspond to this hot temperature being very close to the cold temperature. So it's going to be almost approximately the same, so just a little bit larger. We will see a more relevant example where this is the case. But this already gives us kind of the main ingredient, which is that, so we have like an overall interaction Hamiltonian that's energy conserving, and you want it to be biased in a certain way, right? The Hamiltonian itself must be perfectly symmetric, so it must have both terms, like the green and the red, but we want one of them to happen more. And the way we did this here was by just like changing these temperatures of these two initial qubits to be one slightly larger than the other. Now let's see a more complicated case. So now let's see, suppose we have 3 qubits, okay? So now we can have 3 different energy gaps, and we can have 3 different temperatures. And I'll give you one interaction Hamiltonian. There's not too many options. And for it to be kind of energy conserving, we're going to manufacture the gap such that it's like this. So there's one of them is going to have a larger gap that equals the sum of the other 2. Because then my interaction Hamiltonian is going to be E1 goes up, E2 goes down, E3 goes up. For this to be energy conserving, of course, what goes down must be the same as what goes up. Hence this. Plus the conjugate, right? So this one goes down, the second goes up, and this goes down. Okay. Good. Now let's suppose for now that we want to favor the green transition. Okay. And I'll explain later why. And I can tell already that this will tell us that we want this temperature to be the hotter one. So you can see what the initial state is in order for the red transition to work. So this is going to be divided by the 3 partition functions, of course. And then the only state that's excited is the second one. So it's this factor here. On the other hand, for the green transition to start, Then we need to start here excited, ground, excited states. So it's the probability of the first one being excited times the probability of the last one being excited. Okay. So again, for the green transition to be the favored one, we need this number to be larger than this number, right? So there it is. And now this means that this functions is just, now it's just math, right, at this point. So K is the same for all of them, and the E is the same for all of them. So this results in this condition. E1 over T1 plus E3 over T3 is E2 over T2. And here I just replaced E2, which are conditioned from energy conservation. Okay, so if we have this, and again, for the engine to be reversible, then these need to be very, very close. Okay, so we want this gap to be to be as small as possible, in order for it not to have many leaks. And we'll see this explicitly later on when we can model the couplings. So what is happening here? If we have the green transition being favored, look at this. So there's energy going from the hot, and a little bit of it goes to this cold bath, but because this gap is larger than this, then there's energy kind of in excess. So what will happen is that it will lower the energy of this one. Okay. Right? So it's like there's heat flowing from this qubit to this qubit, but because this energy gap is like even larger than what the heat was from, we need some, it needs more energy to make up for this, so that energy comes from there. So if you have this running for long enough, and you have this one coupled to a cold bath, this one coupled to a hot bath, so that kind of these states are always reset to the thermal state. It is always reset to the thermal state after a while. So you can think of it like, I turn on this interaction, then I stop the engine, I reset this state, then I turn it on again, then I stop it, then I reset this state. Okay, but in reality, that's not what we do. We'll just like always have these couplings running and always have this interaction running. So if this is the case, but this one is not coupled to anything, so it was initially, what this engine is doing is kind of cooling down this system, right? So it's taking energy from this system. So essentially what this engine is a fridge that takes energy from a hot bath, uses another cold bath to cool the system very, very much. So this is a kind of the smallest fridge one could conceive, and it's essentially only 2 qubits plus the qubit that you want to cool down. Okay, but now suppose that we want to favor the red transition because we want to kind of raise the energy of this system here. Okay, because that's what work is. Work is to raise the energy of a system. Well, then let's not stop here. Let's then have, instead of just having 1 qubit here, let's go back to our battery. Have many, 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 many qubits here. Okay. And now, what is a Hamiltonian that conserves energy? An interaction Hamiltonian that conserves energy is going to be kind of the same. So it's going to be exactly the same as this, but generalized for there being many states here, which means that whenever I have 0, I replace it with state I of the engine, and whenever I have 1, I replace it with state I plus 1 of the battery. Sorry. Okay. So here it is EI, and here is EI plus 1. And then I have to sum over all i's. But again, so this red transition corresponds to this goes up, this goes down, and here, if I was there, it goes up there. If I started here, it goes up there. If I started there, it goes up there, and so on. Okay. So it goes from EI to EI plus 1. And the green one is, I lowered the energy by 1 level here. So I push someone down the ladder 1 step. And as a result, I can go up here and down there. Okay. So now, okay, what's the probability for the red transition to happen? So in the first system, it doesn't matter because we have here a sum over all i's. So over all states. So in the end, it doesn't really care about the population of each individual I because we sum over all of them. So you're going to get one. So you just need the probability that this is up and this is down, okay, which is given by this. So this E2, what matters is this. And for the green transition to happen, it's the other way around, right? So this is down and this is up. So the thing that matters is this. So in order, if we want to favor the red transition, then we need this number to be larger than that. Okay, there we go. These partition functions are the same. So this results on T2 over E2 being larger than T3 over E3. So overall here, in this case, it's the other way around. So this is going to be our hot body, and this is going to be our cold body. Okay. In the other case, look, in the fridge, because what we wanted was to cool this one, then the one with the larger energy gap had to be the cold one, right? So that this required a lot of energy to go up, so we could take that energy from the system we wanted to cool. Now it's the other way around. Now we want to give energy to this extra system, my battery. So I need this system to be very likely to be excited, which means that it must be hotter than that system. That's the cold one. And it's going to be, again, the same. So in order for this engine to be reversible, then the gap between these two quantities must be very, very small. So ideally, they would be the same. Okay, so even without looking at the explicit dynamics of this battery, I don't know how fast, sorry, of this engine, I don't know how fast it works, for example, because I don't know like the strength of the couplings, like how this is connected to the hot bath, how this is connected to the cold bath, etc. I don't know what gamma is here, like what's the prefactor behind this interaction Hamiltonian. So I can put here gamma, for example. Good, but I can already say some things about the efficiency. Okay. So what do we know? Well, we know that if the engine is reversible, then these things are approximately, these two terms are approximately the same, right? And we know that if the engine is reversible, that all the energy, there's no energy stored in the form of kind of correlations between the systems, which can be a problem for larger engines. But in this case, all the kind of energy that goes into the battery is going to be the energy that left the hot qubit minus the energy that went into the cold qubit, right? So it's going to be the heat flow from the hot minus the heat flow into the cold. That's what RW is, just like in the classical case. Okay? And what we know, well, although we might not know the exact probabilities of the red transition and the green transition, we know that the energy ratios satisfy this constraint, which means that if something is going here, then it must have gone down there and up there. So the ratio between work and the hot heat and the heat to the cold bath, they must satisfy the same constraints as the energy gaps here, right? They must satisfy the same ratio of the energy gap. Right? So it doesn't matter what probabilities of going, the probabilities are going to be the same of like going up here, down there, and up there. So at the end, they're going to be like this times some probability or some rate. Okay, but for now, we just care about these ratios. Okay, so let's put all these things together. What's the efficiency? So it's work divided by the heat that comes from the hot qubit. But work, as we saw in the best case scenario, is the heat that goes from the hot minus the heat that goes into the cold. And because of these ratios, we can replace them with the energy gaps here, right? Even if this is all times some R, when the divide is the same. And now we can use this relation here to say, well, this is approximately then T2 minus T3 over T2. So the temperature of the hot minus the temperature of the cold divided by the temperature of the hot. But this is the optimal efficiency of a heat engine, like we saw in the reversible case in the previous lecture, right? So this kind of tells us that even this engine that is so small can in principle achieve this optimal efficiency. Now, in order to truly believe this, we need to have this complete calculation of the efficiency and of the work, and also how dispersed the work is going to be in the battery at the end of the day. Okay, but for this, we need to have a picture of the full dynamics of the engine. So we need to model this coupling to the baths, which we don't have the tools to do yet. Okay, we'll do this next time. Okay, but I can already tell you that if we engineer like this energy gaps properly, then this work is going to be much larger than the dispersion in energy in the battery. Okay, good. So this is all we wanted to say for today. So let's just finish with some notes. First of all, these engines are autonomous in the sense that we don't need to go and control them and like apply unitary, then apply another unitary, and so on. All we need to do is to kind of turn on this interaction Hamiltonian by turning on some, for example, magnetic field, and turn on this coupling to the bath. We wait some time, and then we come to check the results. Okay. The other thing is that the most efficient engines will always be very slow. Okay, so this means they have low power, which means that the work divided by the time it takes to reach that much work, it's going to be very small. So this is also the case in classical thermodynamics. If you want to really use all the energy, you need to do transitions very slowly. Okay, so there is a trade-off between efficiency and power. So efficiency and how fast the engine works. But what we saw is that there's no trade-off between the size of the engine and efficiency, right? The first heat engines that existed, these were really things like like what goes inside the locomotive of a steam train. Okay, so very large systems that use, boiling water and coal and so on. And here we saw an engine that is made only of a couple of qubits and which can in principle reach the same efficiency. The other thing is that this efficiency sort of justifies our choice of thermal state as being of this form, because we all started by saying that from reversible heat engines, we can define the temperature of a bath from just the efficiency of reversible heat engines. And in this case, if we define the thermostats like this, we found out that we got the expected efficiency. So it kind of justifies a posteriori that this is maybe a good model for the thermostat. It's maybe not the only good model, but together with the other properties of the thermostat, it kind of isolates it as the only state that makes sense. Okay, so this is all we want to do today. For next time, we're going to look into an implementation of Landauer's principle, which will not be autonomous. So there we really do individual gates, but will give us this bridge between information theory and thermodynamics. And then the only thing that's left to do in thermodynamics will then to look at how we can model a coupling to a bath, and in general, how to model kind of open system interactions. So not unitary interactions, but interactions that are described by a map. What's the equivalent of a Hamiltonian for these cases? Okay, so I will see you soon.